Welcome to this explainer. Today, we are bridging the gap between human biology and astrophysics. We're going to dive in and figure out the true nature of what we actually call sound. Let's kick things off with a pretty bizarre reality. Imagine a massive star exploding out in deep space. You've got this colossal flash, right? Unimaginable energy being released on a scale that's honestly hard to even wrap your head around. But if you were somehow floating right next to it, you wouldn't hear a thing. Absolutely nothing. Why is it that here on Earth we can hear something as faint as the rustling of leaves, but in space there's just this absolute deafening silence? Well, let's break down the physics. Here's our roadmap for today's explainer. 1. What is sound? 2. The mechanism of human hearing. 3. Pitch and volume. 4. Why space is silent. And 5. The hidden sounds of the universe. We'll trace the fascinating journey of a wave from the air right around us all the way out into the void of space.
All right, Section 1. What is sound? Visualizing the invisible wave.
The absolute most important thing to grasp here is that sound isn't a physical object. You can't reach out and grab it or put it in your pocket. Sound is a wave. Specifically, it's a flow of mechanical energy. When an object vibrates, like plucking a guitar string, it pushes the air molecules right next to it. And for that to happen, it absolutely needs an elastic medium, like a gas, a liquid, or a solid, to actually travel through. To really visualize how this works, think of a massive, dense crowd of people. If one person at the back gives a strong push, that momentum ripples all the way to the front. The people themselves aren't running across the room, right? Just the push is being transferred. Air molecules behave the exact same way. They just bump into their neighbors to pass that wave of energy further along. So the crucial point is that the momentum travels, but the actual mass of air stays pretty much where it is. Moving on to Section 2, the mechanism of human hearing, the anatomical journey of a wave. So how does that invisible mechanical push actually turn into the voices or the music you hear in your head? Well, it starts with our outer ear, which basically acts as this perfectly designed biological acoustic antenna. It catches those invisible waves of compressed air and funnels them straight down your ear canal until they crash into your eardrum, forcing it to vibrate. And here is where the biomechanical magic really kicks in. The eardrum's vibrations hit 3 incredibly tiny bones: the malleus, the incus, and the stapes, or, as you might know them, the hammer, anvil, and stirrup. This miniature little lever system is brilliant. It takes those relatively weak air vibrations and amplifies them, turning them into mechanical movements strong enough to push the fluid packed inside our inner ear. Which brings us to the final step. Deep inside the inner ear is the cochlea, lined with these highly specialized, microscopic hair cells. As the fluid inside ripples, those tiny hairs actually bend, popping open ion channels. Suddenly, that mechanical energy is converted into a lightning-fast electrical signal. Your brain then decodes these electrical flashes instantaneously as your favorite song, or a friend's voice, or a crack of thunder. All right, Section 3, pitch and volume, the rules of earthly sound. Let's just quickly cover how we measure the sound we're bathed in every single day. This range right here is crucial. Normal human hearing only captures vibrations between 20 and 20,000 hertz. That is our highly specific biological window. Anything outside of it, like ultra-low infrasound or super-high ultrasound, literally just doesn't exist to our ears. Now notice the difference in frequency. The speed at which a wave oscillates directly determines its pitch. If you have a ton of vibrations every second, you get a high-pitched sound, kind of like a bird chirping. On the flip side, fewer vibrations create a deep, low-pitched sound, like hitting a heavy bass drum. Volume, on the other hand, is dictated by a completely different parameter called amplitude. Think of amplitude as the sheer physical energy and pressure behind the wave itself. You can have a whisper and a scream that are technically at the exact same pitch, but that scream is packing drastically more physical energy into the wave. Section 4. Why is space silent? The cosmic vacuum. Okay, armed with our knowledge of waves and mediums, let's zoom back out to the cosmos and solve that mystery from the very beginning. The contrast between Earth and space is just absolute. Our planet is incredibly noisy because it's packed with atoms and air molecules, which makes passing that momentum super easy. Space, however, is a near-perfect vacuum. We're talking less than 1 atom per cubic meter. With virtually no medium, there is simply no way to transfer those mechanical vibrations. That's exactly why, if you were next to that supernova, you'd only see blinding light. There's nothing to carry the sound to you. Which means, yeah, we have to bluntly bust one of the biggest Hollywood myths out there. In real space, there are no explosive booms. There are no roaring engines during epic starship battles. The cosmos is genuinely, and maybe a little terrifyingly, completely silent. But here's a fun thought experiment. What if you tried speaking on other planets? Well, the varying densities of those foreign atmospheres would totally alter your voice. On Mars, the super thin air would make you sound really high and shrill, almost like a piccolo. But on Venus, with its incredibly thick, hot atmosphere, your voice would drop way down to a deep, bassy timbre. Bringing us to Section 5, Hidden Sounds of the Universe, Acoustic Anomalies. Now, we've established space is a silent vacuum, but does that mean the universe is entirely devoid of sound phenomena? Actually, no. It turns out vibrations can exist anywhere there is at least some kind of medium, like in giant gas clouds or stellar plasma. In fact, NASA's Voyager 1 recorded these plasma waves traveling through the interstellar medium at 50 kilometers per second. Human ears could obviously never pick this up naturally, but physically speaking, those are genuine vibrations moving through space. And then there's this, which is frankly mind-blowing. Astronomers discovered a supermassive black hole in the Perseus cluster that's literally pushing pressure waves out through hot gas. It produces a B-flat note, but here is the kicker. It's playing a staggering 57 octaves below middle C. That is the lowest sound in the universe ever recorded. Now, to help us actually appreciate all this, NASA uses a super cool process called sonification. They essentially take this huge, imperceptible astronomical data and mathematically scale it, squeezing those massive cosmic vibrations right down into our tiny little 20 to 20,000 hertz human hearing window. It literally lets us hear astronomical data our brains could otherwise never comprehend. At the end of the day, sound is just an invisible wave carrying information through space, allowing us to experience the world around us. But take away that medium, and the universe falls completely silent. It makes you wonder, perhaps the greatest mystery of space isn't what we can see, but what we will never hear. If you loved this explainer and you want more simple breakdowns of complex physics, make sure to subscribe to the Universe Code channel. Thanks for joining us, and see you next time.